this is the second of the two videos that I'm leaving for you. If you have not watched the first one that had the little Venn diagrams on it, make sure you watch that one first. So this is the second one. This is the note sheet that's going through 06. This note sheet you already have because 05 is on the back of it. So if you're wondering where your sheet of paper is, flip it over to the back side. This is your notes for 06. Yesterday we were adding probabilities, and that's what that Venn diagram, the last video was over. This one is multiplying. But before we talk about multiplying, let's look at independent events versus dependent events. Independent is just one event going on and then another event going on, but they don't affect one another. So this would be like rolling a dice and then rolling a dice again. Okay, I didn't shave one side of the dice off in between the two rolls. They are both independent of one another. Now, a dependent event, one event affects the other one. So like, let's say I'm drawing a card. So if I'm trying to get like an ace, my chances of getting an ace are 4 out of 52. And then let's say I want to know my chances then of drawing a 6. I don't know. There are now 4, but out of 51 cards instead, if I don't replace. Okay, if I don't replace the card back in there that I drew the first time. This was an ace, this was a 6. If I don't replace that ace back in the deck, there are now only 51 cards in the deck. Okay, so that would be a dependent event. All right, I'm going to have you right over here, independent with replacement, and this one is without with replacement. That's dependent. So independent is with replacement. If I'm putting the card back in the deck, that would be independent. If I'm not replacing the card, then it's dependent, okay? So to find the probability of two events happening, like the probability of getting an ace and a 6, I just multiply those probabilities together. The probability of getting an ace, which over here was 4 out of 52, and I multiply that by 4 out of 51, the probability of getting the second event to happen, okay? All right, so example 3, they have 3 and 4. One is independent, one is dependent. Okay, let me do this. Now maybe I won't have a delay. Nope, I still have a delay. Okay. Example 3, probability of independent events. A coin is tossed and a number cube is rolled. Okay, these are independent of one another because a coin has nothing to do with the number cube. A coin, what is the probability of landing the coin on tails and rolling a 3? So landing the coin on tails has a 1 out of 2 chance of happening. Okay, rolling a 3 has a 1 in 6 chance of happening because there's 6 sides on a dice, and all I do is multiply them together. So I have a 1 in 12 chance of getting a tails and a 3 when I roll a dice and flip a coin both at the same time. Okay, so 1 in 12 chance of that scenario happening. All right, now dependent events, this is when you're not replacing. Okay, a bag contains 12 red, 9 blue, 11 yellow, and 8 green marbles. Okay, whenever I see that, I automatically try to think about what they would be added together. So 12 plus 9 is 21. This would be 32, and 32 plus 8 is 40. So I've got a total of 40. And I haven't even read to the second sentence, but I'm guessing that they're going to need the total. So if 2 marbles are drawn at random and not replaced, what is the probability that a red is drawn and then a blue is drawn? So red, there are 12 out of a total of 40 times a blue marble is drawn. There are 9 blue marbles. And now, if I don't replace them, there's only 39 marbles. Okay, so 12 over 40 times 9 over 39. And then what you can do is, if you can reduce any of these, that's a good idea to do before you multiply them. So 12 over 40 will automatically reduce. If I divide both of them by 4, this becomes 3 and this becomes 10. So, oh, and then 3 and 39 will reduce. So this becomes a 1 and this becomes 13 when I reduce them. And I think that's all I can do. Yeah. So 1 times 9 is 9, and 10 times 13 is 130. So I have a 9 in 130 chance that if I draw 2 marbles, or 1 marble right after the other, The first one will be red and the second one would be blue. Okay? All right, now moving on to conditional probability. I have so many kids that screw this up a lot, so pay attention to this because this is important. All right. Make sure the baker's up there. Here we go. Okay. At a restaurant, 25% of the customers order chili. If 4% of the customers order chili and a baked potato, find the probability that someone who orders chili also orders a baked potato. Okay, now the underlying determining factor here is 25% of the people are ordering chili and 4% of the people are ordering both. Okay, find the probability that someone who orders chili also orders a baked potato. I start with the chili part. Okay, there's 25% that's ordering chili, 25%, and I put that as my bottom number because that's like kind of like my total. We're talking about the total people who order chili. And then we're saying also order a baked potato. So now we're focusing in on the top number and we're figuring out how they are in relationship to the total 25%. So 4 over 25, you can reduce that and figure out what that is as a decimal, and it's like 0.16 or something. So 16% of the orders are of the chili orders are also baked potato. Okay, that one was kind of difficult to understand because it was percentages. All right, this two-way frequency table will make it a little bit easier to understand. So, a two-way frequency table: a drug company conducts an experiment to determine the effectiveness of a certain new drug. Test subjects were randomly assigned to one of two groups. When you're doing stuff in science, a lot of times you'll use this method of testing like supplements or drugs to see if they are working, and it's called a double-blind study. So basically they give some group the treatment, that's the treatment group, and then somebody else they give a placebo, and a placebo is basically like a sugar pill, and they do that so that the two groups don't know if they're getting the actual treatment or they're getting the sugar pill. Okay, so that prevents somebody from saying, yeah, I'm feeling so much better, when they actually got a sugar pill. Okay, so it's to try to eliminate anybody from thinking they're actually better when they're not, or to thinking the drug is not working when it actually is. So, so treatment group, control group. So in the treatment group, given this drug, I had 1,600 people say that the condition did in fact improve, and 400 said that I didn't feel better at all. In the control group, I had 1,200 people say that their condition improved, and 800 say that they didn't feel a thing. Okay, these people right here are the crazy ones. They're given a sugar pill and they're saying, yes, I feel so much better. No, you don't. You're given sugar. So these people should not be feeling any effects because they're not being given anything. So that's kind of the breakdown of this table. It says, for part A, find the probability that a test subject's condition improved given that he or she was in the treatment group. Now, I always start with after the given. Now you can't see this. Start with the given. And that's the bottom. That's the bottom number. In your probability, that's the bottom number. Given that he or she was in the treatment group. Okay, so now we have to look and see how many people were in the treatment group. Well, 1,600 was in the treatment group, but so was 400. So together, there were a total of 2,000 people in the treatment group. Given that they were in the treatment group, 2,000 goes in the bottom. Now, I'm interested in finding the probability that the test subject's condition improved. So of those 2,000, which ones actually improved? That would be the 1,600. So 1,600 goes in the top, given their condition improved, or given that they were in the treatment group, how many had their condition improved. I can reduce that if I drop off a 0 on each one. So that is 16 over 20. As a decimal is like 80%. Okay, or 0.8, I guess that was a percentage. 0.8. That is my probability. 80% of the people that were in the treatment group said that they felt better. Okay, 20% said they didn't. Find the probability that a test subject was in the control group given that given that his or her condition did not improve. So given is here. So I'm looking at what's after the given. Start with the given. Given that his or her condition did not improve. So over here on the table, who all had their condition not improve? These two had their condition not improve. If I add this together, that's 1,200 people said their condition did not improve. And I'm interested in finding, of those 1,200, who were in the control group. The control group was 800. So 800 people out of 1,200 said that their condition did not improve and they were in the control group. That, if I lump off the zeros, that's 8 over 12, which is 2/3, or about 66.7%. 0.667 basically. Okay, so doing these, you want to make sure that whenever it says the given, you start with what that is. Given that his or her condition did not improve, and that's what we put on the bottom. The condition not improving is those two together. And then you work backwards and you go to the other value. Okay? Your assignment is on the board in my room, but if you're not in my room, I haven't figured out yet if you are going to the library or not, so let me write your assignment down here. It is, if my class will move out of the way, Jay Skula. Somebody read algebra 2 to me for Wednesday. 0.6, what is that?
0.6 multiplying probabilities.
Yep.
Page 19, 2 through 16, even.
2 through 16, the evens. There's your assignment. So do this assignment plus do that bubble sheet as far as you can, and then we'll finish and go over questions tomorrow. You should also have the adding probabilities homework assignment. I'm not going to have you turn that in until tomorrow. So we'll go over a lot of stuff tomorrow. All right? So work on this, and there you go.